Imagine you're in this new city and you want to find a path from a place A to place D. You can choose a path that goes from B to D, or you can choose a path that goes to C first and then to D. Now, how do you find the best path or even the shortest path? Now, imagine a different scenario where you're stuck in a maze and you need to find a way out. How would you go about finding an escape path? Now, these are exactly the kind of questions we'll be answering in this video series about graph theory and its applications. So let's dive in. Hi, I am Piyush, and in this video series we are going to explore graph theory and its applications in computer science. In this particular video, we are going to cover the fundamentals or the basic building blocks for graph theory. So let's get started. Now, before solving graph theory problems, let's take a step back in history and understand where it all actually began. Now, it all started in 18th century Königsberg, where there were 4 parts of the city divided by 7 bridges, and mathematicians tried to find out or find a solution to a particular problem which we now call as the Königsberg Bridge Problem. The rules of the problem were quite simple. You can start from any part of the city and you must traverse all the bridges. You can only traverse a bridge exactly once, and you must return to the place where you started from. Sounds simple, right? But unfortunately, whatever path you take, it seemed like a solution to this problem didn't exist. You can take a different path, but it seems like you have to cover a bridge twice in order to either cover all the bridges or even to complete a cycle. But how do you find a path, or does a path like this even exist? Does a solution to this problem even exist? Now, Euler in the year 1736 did something remarkable with this Königsberg Bridge problem. He reimagined the problem by representing the parts of the city as vertices and bridges as edges, essentially converting the puzzle into a graphical structure that marked the beginning of graph theory. Euler also noticed that if you have an outgoing edge from a particular vertex, or basically a bridge from a particular part of the city to another part, you must have a corresponding incoming edge that points you back to that part of the city. That means that each vertex must have an even degree, where a degree is simply the number of edges connected to a vertex. Now, a cycle that satisfies this condition is now known as an Eulerian cycle. And sadly for the Königsberg Bridge problem, such a cycle does not exist. But here's something interesting. If you just remove 2 bridges, you can find a path that works. Now that we have taken a look at the history of graphs, let's ask the obvious question. What exactly is a graph? Now, we all know that graphs are, nodes and edges, right? And they have some kind of relationship between them. But what exactly are they? Why do we represent them, and what does it signify? Let's break it down with a simple example. Imagine you're on Facebook and you're friends with a particular person B, and we can denote this friendship with an edge between you and B. Let's say B is also friends with a particular person C. Now this represents a friendship graph where A and B are friends and A and C are friends of friends. Now we can convert this representation to something we are more familiar with. A graph with vertices and edges. Now in general, a graph is denoted by G, where V is the set of vertices and E is the set of edges. For this particular representation, V is the set of A, B, C, or the set of vertices, and E is the set of pair of vertices. Now we have already looked into this representation before, and this graph is also called a connected graph. What I mean by that is, if you select any pair of vertices, there is a path that exists between them. You can also have a disconnected graph where some part of the graph might be isolated from the rest. You can also have a strongly connected graph or complete graphs where if you pick any pair of vertices, you will have an edge between them. Now this kind of graphs are also called as undirected graph, which simply means that if you have an edge xy in the edge set, you will have a corresponding edge yx in the edge set as well. For example, let's expand this edge set. If the graph has an edge a, b, that is an edge between A and B, it will have an edge between B and A or B comma A in the edge set as well. Now we also have directed graphs where if you have a particular edge A comma B in the edge set, it's not necessary for the edge B comma A to exist as well. Now that means that we can only traverse from A to B in the graph and B to C, but not the reverse. Now where does directed graphs become useful? Let's take a small example where we have 4 routers that wants to share data between them. We can actually use a directed graph to represent the data flow. For example, over here, we can see that A is sharing data with B and D, while B is sharing data with C and D. Now we can also add latency or weights to the edges to signify the latency between the routers. For example, if we take the edge A comma B, this denotes that the latency for data transfer from A to B is 3 milliseconds. We can actually use this to find out the data transfer latency between A and C by just summing up the weights. Now that we have looked into some graph representations in general, let's explore some other variations of graphs. We have already talked about simple graphs, where each pair of vertices has at most one edge between them. Then we have multi-graphs, where multiple edges can exist between the same pair of vertices. You can think of multiple routes between two cities with varying distance. We have also seen directed graphs, where edges can have a direction. And finally, there's one more variation. It's just a special case where you have a graph with a loop where a vertex can have an edge to itself. Nothing really special. Now, before we jump on to discuss how graphs are represented in the computer, let's first try to answer a question on graph which will be crucial for analyzing time and space complexity later. How many total edges can there be in a simple graph? Or to rephrase the question, how many edges can there be in a strongly connected graph? For example, a strongly connected graph of 3 vertices will have a total edges of count 3. A strongly connected graph with 4 vertices will have 6 total edges. And a strongly connected graph with 5 vertices will have 10 total edges. Now, do you see the pattern over here? To generalize this, the total number of edges for a graph with n vertices is basically nc2. That is, if you have n vertices, we are trying to find all the combinations of selecting a pair of vertices from the vertex set to assign an edge. Or in other words, it determines the total possible unique pairs of vertices we can select. Now that we have explored the fundamentals of graph theory, let's dig a little deeper and see how graphs are represented in computer memory. We'll take a look into 2 of the major representations, adjacency matrix and adjacency list. Let's start with the matrix representation. For this representation, we'll transform this graph into a 2D matrix representation where the rows and the columns of the matrix denote the vertices and the cell value indicates whether a particular edge is present between the pair of vertices. For example, over here, the diagonal elements are set to 0, signifying that there aren't any loops. And if there is a connection present between any pair of vertices, we represent them by 1 and the rest as 0. Now in computer memory, we typically index rows and columns starting from 0. So for simplification, we will convert this graph with nodes ABC to 0, 1 and 2. And the resulting matrix representation will follow this 0-based indexing as well. Now we can also use this for representing directed graphs, where we have 1 only in the cell where a directed edge exists. For example, over here, vertex 0 to vertex 1 have a directed edge, and so 1 is present in the 0th row and first column. Now, if there is a weighted directed graph, we can simply replace the ones with the actual weight of the edge in the matrix itself. Now, one important thing to notice over here is that in the matrix representation, we are actually storing values for every pair of vertices, even when there's no edge between them. So if the number of edges is relatively small compared to the number of vertices, this approach might not be that space efficient because the space complexity is big O of n squared, where n is the number of vertices. Just note this point as this will come handy later. Now let's have a look at another representation, adjacency list, where instead of a matrix, we are using a linked list or a dynamic array to represent the edges or the graph in general. So in this representation, we have a dedicated list for each of the vertices, and we add a node to a particular list only if an edge is present. For example, if we considered vertex 1, which is connected to vertex 0 and vertex 2, the linked list for vertex 1 is connected to node number 0 and node 2, denoting that there is an edge present between 1 and 0 and 1 and 2. Now, if we have a weighted graph, we can store the weight along with the vertex in the linked list nodes as well. One major benefit of having an adjacency list is that the space complexity is big of V plus E, since we have a dedicated linked list for each of the vertices, and each of the nodes in the linked list represents an edge. But let us actually compare these two representations to get a better idea of when to use what. Now we have seen two representations, an adjacency matrix and an adjacency list. Now we have also explored the space complexity, which is big of V squared, where V is the number of vertices for the matrix representation and big O V plus E for the adjacency list representation. Now the matrix representation will be really useful when you have to quickly check if an edge exists, since you can easily represent the pair of vertices by the row and the column, and you can search for the edge in constant time. While in the adjacency list, you have to go to that particular node and scan through its list to find if the edge is actually present. In the worst case, it might go up to big O of E. So, when do you actually use a matrix or a list? Well, it depends. But if the graph is dense or has a lot of edges, a matrix is generally useful. Even though it consumes more space, it gives you a faster edge lookup. But if the graph is sparse, or in other words, it has lots of vertices but relatively few edges, an adjacency list will make more sense. It's much more space efficient, though edge lookups are kind of slower. In practice, as we will see in the next video, adjacency lists are used most commonly in graph traversal algorithms like breadth first search and depth first search. And that brings us to the end of this video. I hope you liked this video about this informative content on graph theory. In the next video, we'll explore and dive a little deeper into understanding graph traversal algorithms using these building blocks which we covered today. So see you in the next video. Be curious, stay happy, bye.